software. So first thing I need to do while IntelliJ is loading is that I'm going to go through this and show how to get this working. So I'm going to go ahead and, let's see, go into, I'll put it in my desktop. Come on, new window. There we go. Recording takes a bit of a, and loading multiple things does take a bit of a hit, especially when you're loading something like IntelliJ, which is actually pretty hefty. I actually plan on totally wiping this computer again. Let's see. Come on. You can do it. So let's go ahead and see what I need. So Jung is located on SourceForge. There's a new version on GitHub, but but it works a bit differently, so I don't know. This is the one I'm using, and it's still active. So until then, it just works pretty fine. So you want to go ahead and download it here. Also note, very important, if you get stuck, this third page documentation has a couple things. First, the API here, which is a list of all the things that Jung has. The most important things are what can you do with a graph, literal. So we can look for the graph class over here. Okay. Right, this is specifically the graph interface, and what can we do with a sparse graph? All right, so basically what does a graph, what methods do we get from having a graph? So we can add edges, get destination, get the outgoing edges, get the amount of predecessors, get the source, get successors, get the in degree, which is useful for your next homework, by the way, get your out degree. So you can also use something to get a collection of edges, just an abstract collection. You don't know if it's a list or anything, but you can always iterate through it using a for each loop. So you'll be using that plenty today. Regardless, though, you may be wondering, okay, but this is new. How do I put it together? Generally, something saying it's a tutorial is pretty useful. So this thing, Jung 2.0 revision, and it has a working program to start right over here saying, hey, put this in and this will create a graph, and this is the output saying the graph has vertices 2, 3, 1, and here are the edges. How do you make custom edges if you need weights? How do you do graphics with this thing? Because you can totally do graphics. So, all right, now that IntelliJ has stopped being, or I thought it would stop being shy. Come on, IntelliJ, you can do it. All right, so new project. We're just going to go ahead and do this as a new project. Next, graph demo. So I'm just going to show you how to do this because I've already got it inside my own, inside my repos. So new graph demo. Okay, new. So here we've got our classes and stuff, and let's just go ahead and just make a class called graph demo, right? Now obviously I can't just go public static void main and then do the following graph, and I'm just going to go string to string. For right now, is a G is equal to a new sparse graph, because guess what? It doesn't know what any of those are. It doesn't know what a graph or a sparse graph is. It doesn't know where to find those. I can't even import them from the right place, right? It's just, so that's because I don't have the libraries for this. So where can I get those libraries? right? I get them from downloading them. The whole download all Jung releases here. So I'll go to this one, click on Jung. Actually, wait, there's a latest version over here. Download, I'm going to hit that. We'll start shortly. I'm going to go ahead and open it, and I'm going to extract these to, I'm going to go ahead and make a new folder on my desktop because I don't have any. Show me the files. Oh, wait, no. I just extracted one of them, so let me go ahead and extract desktop, new folder. I'm going to call it jars over here, and I'm going to extract them all into jars. So now if I show the files, boom, they're all in this folder, right? So what are jar files? They are short, .jars are short for Java Archive, which is actually not really any special file. For instance, if I open it in an archive manager, it's going to essentially be able to read it like it's a zip file. And so let me go ahead and just open up, because that's essentially what it is. It's a zip file, but you're telling the program that it's actually got Java stuff in it. It's one way to get an executable to somebody else. So if I go to the Jung if I go to the Jung, yeah, let's try this, API. So it goes, it's in the edu package, the UCI, the ICS, the Jung, the graph package, and then it has class files, not Java files, but Java class files. In other words, here's the compiled Java code, which anybody who has a Java virtual machine can run. Didn't give us the source code, that's somewhere else. We don't need the source code if we're just using it as a library, right? Now, we don't need to do anything special with these libraries to use them. If you're just simply like putting them up somewhere on a, if you're just basically creating a project and you're like just using something like Vim or Geany or just some other basic text editor, you can just toss them in the same directory as your Java files. However, if you're using an IDE, it expects things to be done differently. And I've done it for NetBeans, and I have a demo online for NetBeans, for IntelliJ, and for Eclipse on how you get all the files where they need to go. But I'm going to show you guys here anyway how to do that. So, so it's fairly straightforward. All you have to do is we are going to go to desktop, go to jars. I'm going to grab these all, Control A, press Control C to copy them all, or you can do Control X, doesn't matter. And then I'm going to go over here to the top level. Notice where I click, the top level of my directories over here. And I just press Control V, and it will copy those, and it says, oh, you want to copy those files? Great. And now I'm going to go ahead and select all those files except for this guy over here. And now I'm going to say, hey, I want to add these as a library. In IntelliJ, that's how you do it in IntelliJ. You're basically saying, hey, these aren't just files hanging out here. I want you to actively analyze these files and use them. If you're in Eclipse, you do pretty much the exact same process. The only difference is you click an option that says add to build path, and it's under the build path menu, I think, on there. And so you just simply say these are project libraries. They only exist in this project. And boom, you notice that there's some arrows there, and it's starting to analyze this now. And so, and then now when I do this, where it says, hey, these are graphs, it says, oh, you can import the class. And look, it popped up. EDUs, UCI.ICS.Jung.graph. That's how I find that. But now it's compiling it just fine, right? So it's pretty much an instantaneous process. It's basically, so this is how you can just get stuff from Java. You can just simply grab it from, so that's how you get a lot of libraries that you might need. You import them into the stuff. And the reason where you're going to be using this is that it's much easy, is that implementing graphs is a bit of a pain. And also I want you guys to learn how to actually, use an external library, because that seems like a useful skill to know. So now that we've got a graph, we can essentially do stuff with it. Like we can add edges to it. So I'm representing the node. So what this means is I'm representing the I'm going to switch this to integer and string. This means I'm representing the nodes with integers, okay? And I'm representing, and so every node in the graph has an integer indicating what its name is, and every edge in the graph has a string indicating what its name is. So for instance, I want to add an edge between the nodes 4 and 5, and I want to call it, let's see, I want to, oh sorry, other way around. I want to call the edge, I want to add the edge A between nodes 4 and node 5. Nodes are also called vertices, but I like to call them nodes because I come from a networking background. And so now if I, and note that node 4 and 5 don't exist yet, but if I print out the graph now, building it, it will run it in a bit. See, does this actually do anything? High performance? So now if I run this, it says, hey, vertices are 4 to 5. The vertices in this graph are 4 and 5. And there's an edge called A, which goes from 4 to 5. Right? And so now if I add another edge, g.addEdge A, if I add edge B from 4 to 6, that means that 4 is connected, 4 and 6 are now connected, okay? And, sorry, I've been programming in Python a whole lot these days. So, now if we run this now, yes, I know, but that was from the last build. Run it. It will now say that I've got edges 4, 5, and 6, and there's an edge A that's between 4 and 5, and an edge B that's between 4 and 6. Right? Okay. And the nice thing about this is that we can actually display this graphically in Young. Now, you don't have to do any graphics, by the way, in this, but I think it's pretty nice to do so if I'm teaching you guys to just be able to display it. You know, so visualizing graphs over here. So simple graph view. So I'm just going to copy this. And I remember this being a bit of a issue to work out the first time I did this, but I have a working program somewhere. All right. So Control V. Oof. Okay. Simple graph view is equal to new simple graph view. Okay. Oh, it's called, oh, okay. I understand what it's saying. I understand exactly what's going on there. There's no need for that line over there. Okay. Next. Okay. Layout is equal to, okay, graph demo. So I'm going to just do this so we can visualize the graph. You don't have to worry about this part. Graph demo D is equal to new graph demo. I just want you guys to see what's going on. Import that D.G. A new circle layout of, actually we just need to put in G. That should work. And layout, set dimension. Yeah, it's amazing how much just actually importing it fixes stuff. Yeah, sorry about this. You can copy paste it from the tutorial, but copying from a PDF sometimes is less than awesome. Yeah. Oh, missed that part. So now these are just the graphics in Java can be a bit of a pain because I don't know, it's annoying. I don't want to debug it. I just want to run it. Okay, so now if we run this graph, notice that we've got ourselves a graph, right? One node connects to another. Now, labeling these things actually requires us to actually do more code. But if we add another node, let's go ahead and add another node to connected to 4. G.add edge. E to from 4 to 1. And again, it will automatically create that node, that vertice 1 over there. And just to show that, we also have a g.add vertex, which adds a, we can add a node, let's call it 20. And we can go ahead and run it. And we get 1, 4, 20 there, and then here's our edges, right? So this is node 4, it's connected to 1, 5, and 6, and here's node 20 without any connections, right? So this is so basically, though, this is the important bit, the text over here. The big thing is that the edges are set. If you try to add a vertex, right, the same vertex in, so here I'm trying to add 20 twice, it just rolls with it, I believe. Yeah, it just rolls with you adding 20 again. That's fine. No worries there. It's like, it's a set, essentially. But if you try to add an edge and give it the same edge name, you'll get an error. Right, it says that edge already exists. So there's 2 ways that I find to keep you safe while doing this, to avoid that error. The first is to not use like string or something, but actually to create a private edge class, right? And then, you could create a private edge class, so like private static class edge, right? And it will be identified by its toString, I think. It goes into detail about how to do it in here, right? It just kind of gives you an example over here about how to make a edge class like myLink, and then all it needs is a toString. Let's see. And it will make, I think what it cares about is that ID method over there, but honestly it's the toString that really helps with it. But regardless, the other way you can do it, and the way that I find the easiest way to do it, is that I just simply, whenever I'm adding an edge, if I'm adding an edge between 4 and 5, I call it 4, 5. If I'm adding an edge between 4, 6, I call it 4, 6. If I'm adding an edge between 4, 1, I call it 4, 1. Make sense? Right? And that way, that will help on the next assignment. So this assignment, you're trying to do breadth first search, where basically and depth first search, where I basically want you to print out all the nodes in the order that you find them, either using breadth first search and depth first search. Now you've done depth first search already, all the way back when you did the maze assignment. That's not that difficult of a, you can pretty much use the same thing. So depth first search can be implemented recursively. I find it much better to implement it using a stack. And essentially for these searching algorithms, you want to use, for depth first search, you want a set of unvisited nodes, you want a set of stuff you've seen, and the set of stuff that, so you really just need the stuff that you've seen so far to make sure that you're not going to be visiting anything twice. And then you also want basically to have a list to hold your output, right? So this is the order I'm visiting stuff in, and then having a stack so you can backtrack. Breadth first search works almost the same way as depth first search, except that you're going to be using a queue, and you're going to be adding things to a queue and dequeuing from the queue to figure out what the next place to go is. So they work very subtly differently, but they have different objectives. So you guys can go ahead and get started. I want to help you get started with this if you need help, like getting, Jung working, or if you're trying to get NetworkX working. But I'm there to help. Yes.
Just one thing. How do we actually say we're at the root, or say we're at a given item?
Excellent question. So just give it an arbitrary node to start with. There is no root in a graph.
Okay.
So we just give it an arbitrary starting node and say that we're going to start a breadth first search from here. Yes?
What are we returning? Are we returning like a path to a desired node?
No, I want you to output basically the order in which you traversed stuff.
Okay.
So
Could we just see a code, when you say start with a given node, does that mean since our type's an integer, it's 0
Yeah.
neighbors?
You could start from 0.
Okay.
Now to get the neighbors of a node in IntelliJ, if you want to get, that's an important point over here. So if you want to get the neighbors of a node over here, this function over here is very useful. So you would say, so whenever you want to interact with the graph, you're never, or you want to get a vertex or get an edge, you're always interacting with the graph. So you'll say g.getNeighbors of node 0, and this will return a collection of all the nodes in node 0. Now, collection, again, it could be anything. It could be a set. It could be a list. I have no idea. But since it's a collection, it is iterable, which means you can iterate over it using the for each loop. And you can also, I think if you need to, you can. I forget. I think list might have a constructor that, given a collection, you can turn it into a list. But just iterate over it. So your for loops should look like something like this. So let me just go ahead and open up Geany for a second. So suppose we have a graph G, right, somewhere. Your for loops to iterate over so we have a graph G and we have a vertex current, right? Okay. And the idea here is that basically you want to say for v neighbor, right, whatever type that is, in g.get neighbors of current. So for each neighbor in the collection of neighbors, right? And then you can do what you want with the neighbor. Okay? The next thing you might want to do is the way that I highly suggest you implement breadth first search and depth first search as the way you declare the methods is public static, and then you can return whatever you want. You can return a list. I'm just going to put void for right now. Public static, and it's going to be a generic thing. So v and e. So public static ve because it takes into a vertex argument and an edge argument. Public static void. Let's call it BFS, breadth first search, and then graph G, which will have some vertices and edges, right? A graph of vertices and edges. That way you don't have to type integer or string all the time. You can just do v and e, and then it will also work for any kind of graph you get. And then a v start point. If you don't want to give it a start point and you just want it to go automatically, instead what you could do is that if you need a start, you could say v start is equal to, and then what we can do is we can, let's see, get vertices. So that will return a collection, okay? And this is super hacky. But if you're given a node and you just want to start from, if you're given a graph and you just want to start from somewhere, g dot get vertices. Okay, that's going to return a collection of vertices. And then for collections, well, to actually work with it, I'm going to go ahead and turn it into an array. I know, super hacky. So we take the collection, turn it into an array using toArray, okay? Because you can do that with every collection. And then I'm just going to grab the first thing in the array. That looks awful, right? That's why I did it in the comment. So it's much easier to just give you a starting point. But if you don't have a starting point, then you can just grab some random starting point, some arbitrary node as the starting point by saying, hey, grab the vertices, convert it into an array, and then grab index 0 of that array. Okay. So those are the keys there. Any other questions? I'll be happy to just walk around and help you guys get set up so that you guys... And the main point of this is that the next assignment is going to use graphs as well to solve an actual problem. So I didn't want that to be I've never wanted that to be I never wanted you to have the headache of trying to work with the library and solve a problem that's not exactly hard, but it's during the last week of class, So, but it's a fun one. We're going to be cracking a password, so using graphs. All right, so go ahead and get